Animation is the art of drawing in time. This film will show some new ways in which a computer can aid in the process. The computer at MIT's Lincoln Laboratory is the TX2. The animator is Lynn Smith, an artist with no previous computer experience. The animation system is called Genesys. Genesys is a computer program which transforms the TX2, a tablet, stylus, and display scope, into an animation medium. Lynn points with the stylus to the word sketch, which tells Genesys to record her sketching motion. Pointing to another command erases it. No marks are left on the tablet, but all drawings are automatically recorded and filed in the computer memory. Having shown us individual sketches, Lynn will now sketch a sequence of drawings in time. She finishes the first drawing. Then makes a second. And finally, the third. Pointing to the word playback commands Genesys to show her what she's made immediately, instead of waiting days as with conventional film animation. Having seen this, Lynn now wants to try a second example, a bouncing ball. Again, she produces the sequence as in conventional animation, by sketching each individual frame. Notice she draws a squashed ball at the point of contact, a little extra emphasis. Immediate playback dramatically increases the animator's involvement with his work. Is there a way to make a ball bounce that's simpler than drawing each individual frame? With Genesys, there is. Lynn draws one ball and types its name. Now, using a technique known as drawing a P-curve, she shows Genesys how to move the ball by drawing the desired bounce. And here's the result. Lynn has told Genesys to combine the sketch of a ball with the sketch of a bounce to create a bouncing ball. Now, let's look at the P-curve technique more closely. Lynn sketches an alternative motion for the ball, which it then carries out. Genesys records not only the path, but the dynamics with which her hand traces out the path, and to help her, displays the movement as she draws it. Any movement that can be mimicked can be constructed in this way. Bounces or leaps or spirals, zigzags and swishes and zooms. It only takes seconds to try out a new idea. Each movement is a sketch, hence animation becomes immediate and spontaneous. Let's go back to the bouncing ball and give it a little more character. Recall that the original bouncing ball had a squashed cell at the point of contact. Therefore, for the P-curve version, Lynn sketches a second cell and calls it ball 2. To help her put this ball where it belongs, Genesys displays a selection graph that tells us which ball is to be used in each frame. First, she finds the precise instant of contact. Then she trades ball 2 for ball 1 in that frame. Thus, 2 drawings do the work of 10. In conventional animation, a specific motion is always tied to a specific set of images. In this system, both pictures and motions have truly separate identities. Any movement can be freely applied to any picture, so Lynn can apply her bounce to a frog instead of a ball. We brought with us not only a bounce, but also a picture change at the crucial point of contact. Therefore, Lynn can draw a second frog image for this instant in the sequence. But she isn't completely happy with the result. She decides to keep part of Frog 2 and erases the rest. Now she'll make a more radical picture change at the point of contact to try to get a real splat. Genesys encourages experimentation by making it easy to change all or part of a movie, and thereby to alter the quality of the whole. This fluid trial and error isn't possible in conventional animation, but it's natural to Genesys. Let's watch Lynn experiment with the relationship between two objects. She decides to introduce a line to react to the impact of our bouncing ball. The line cell is recorded by a cell directory in the upper left corner. The cell directory lets Lynn keep track of each drawing she uses in a sequence. She sketches a second, bent line cell. Then calls up the selection graphs to help her to synchronize the bending of the line with the impact of the ball. There, she introduces the bent line in each of the 3 frames having the squashed ball. Unfortunately, the objects no longer touch at the instant of collision. To solve this, she finds the first frame that needs correction and aligns the ball with the bent line. She also makes this adjustment in the other 2 frames. Rather than work further on isolated fragments, Lynn now begins to develop a simple story using the ball. First, she gives the ball a new movement, or P-curve. Then adds a second ball to which she applies the identical P-curve. To separate the 2 balls more, she pulls them apart. Lynn wants to give the action a game-like quality, with the second ball reacting in each case to the movement of the first. To understand how this is done, let's look at graphs which describe the horizontal and vertical motions of the first ball. The computer derives these waveforms from the P-curve. Their time axes are lined up. The corresponding waveforms for the second ball are also displayed. Lynn pushes the waveforms of the second ball to the right so that its movements lag behind those of the first ball. She refines the cells and adds other material to finish the sequence. Throughout the work, she makes use of the ability to sketch movements and then to change their timing, rhythm, and dynamics, as well as inserting new cells at key points in the story. The evolution of any scene in Genesys begins with a diagrammatic blocking out of the action. Separate qualities, like layers, are developed in turn. Objects are made plastic, for instance. Then dynamics are refined. Each quality is automatically integrated into the entire scene. The independence of pictures and motions, the ability to apply new movements to existing images, and new images to existing movements, as well as the ability to recall pictures and motions from an expanding library, make experiment easy for the Genesys animator. So far, all the animation you've seen has been done in apparent 2 dimensions. Now let's add a third through varying the size of a cell. That is, drawing P-curves which simultaneously expand and contract the horizontal and vertical coordinates of an image. Different P-curves result in different dynamics. Let's separate the horizontal and vertical coordinates of our P-curve. They're identical, obviously, for simple size change. But we don't have to change the size of these coordinates in phase. We can throw them out of phase, say, height increasing as width decreases, and vice versa. We can apply this to any image. Our ball, for instance. In fact, certain variations can result in the illusion of rotation in space. Planar rotation can also be mimicked with a P-curve. Giving our old friend the bouncing ball both planar and spatial rotation, we get a flipping coin. We can also insert picture change into this sequence, which results in a totally new movie. By combining different kinds of movement and picture change, we get entirely new feelings of space and dimension. In this film, human dynamics determine image dynamics. Unlike film animation, the artist can experiment with images and dynamics in real time, refining ideas until they have a life of their own. The Genesys system is one of the first to exploit real-time interaction between animator and computer. Not only does the animator grow with the system, but the system grows with the animator.